I really forgot. All right, nice. So quickly, just to remember, electric fields, they move away from the positive. Electric fields move towards the negative. Like poles repel, as you will see here. Like poles repel, unlike poles attract. Right? Good. We learned about static electricity and the movement of charge, right? Right, notes time. Let's go to the notes. I'll look at the simulation. It's just to give you an idea of what happens, right? Remember, in static electricity, what's the main thing that causes the static charge? That's one way of getting it, but it's really the movement of electrons, right? Yeah. Huh? It work? I mean, no, that's a summary. I mean, that's a simulation.
No, I mean in notes.
No, I'm not saying that one was it. All right. All right, let's take these small notes here. All right, I don't have your handout as yet. I'll get it back and I'll send it to you, right? The handle electricity. All right, so first thing I want you to do is head up electric fields. Head up electric fields. Electric fields. Right, an electric field is a region. An electric field is a region around an electric charge. An electric field is the region around an electric charge where an electric force is experienced. Where an electric force is experienced. The region around an electric charge where an electric field is experienced. Right, full stop. There are two types of charges, a positive. There are two types of charges, a positive charge and a negative charge. Right, do me a favor, join the positive and join negative charges there. Draw the positive and draw the negative charge, please. And you don't have to draw those dotted lines. Just draw the P lines equally spaced out, and then draw the direction. Electric fields always what? Move away from the positive or towards the positive? And towards the negative, right? Yes. Right. Draw this here for light charges. Sorry, on light charges. Go back. No. One second. 15 seconds. Right. Those are unlike charges. You draw like charges somehow. Those are unlike charges. I want you to draw like charges somehow, please. Well, like charges, direction and important. Very good. The direction important, right? Well, you're supposed to really like those hours that should be in direction. Whatever you like that, yeah. Yeah. Will that interaction happen? Nope. So yes, so the field lines don't interact. So here we have unlike point charges and they attract. Right? And now with the like charges, they will not interact, right? Right, but the direction is important. Electric fields always go towards the negative. Right? You should always highlight this. There's a little region in the middle. There's a little region in the middle called the neutral region. Right? This region here is called your neutral region. All okay with that? Okay, and always remember the direction important, right? They always go towards the negative terminal, right? Towards the negative pole and away from the positive, right? Online, are you okay there, Cameron? Garage, are you okay there? Yeah. Too positive, very good. But what will change? The direction of the field lines, right? Just make a note underneath, like charges repel. Like charges repel. Okay, so you have a positive, you have a negative, you have field lines here. Last one. Suppose instead of me giving you points, point charges, I give you a whole plate. So I give you a positive plate and a negative plate. It looks like that. Right? Electric fields always leave the what? Always leave positive and go towards the negative. And notice, see the field lines? They are equally spaced, right? Okay. Do this next one. Oppositely charged plates. Off. Now it might just walk from there and go in the book. It might. Sometimes it's happen. Sometimes this happen. Yeah. Sometimes this happen, you know. I see that happen a few times already. Yeah. It walked right there and make a little step there and just jump down in the book. It don't always happen. No. Honeyman again, Julia. Call honeyman again, Julia. So now we know what all the felines look like, right? Did I move that off? Everybody okay? Yeah. Nice. So we had the felines there. Good. We had to go back and do some quick little explanations here. Right. So quick little notes. Actually, here's what I'll send this for you so you do it right. Yeah, I want it. All right, I got to send in group, right? Hold on, Right, I'll share it in the group so you don't have to write it. Have a good day. Oh, sure. Sorry. Right. Those who are online, you all got it? This is I send the first part of electricity. Christian, you forgot to message me, right? I know you messaged me earlier, but I can't remember. What's the number again, Christian? $760. I know you just sent my WhatsApp, but I'm not seeing it. Send back a WhatsApp, please. All right. While you're waiting there, the next thing that we have to look at is just run through these things that we know already, right? So in electrostatics, there are two types of charge, a positive and negative charge. A fundamental quantity E, 1.6 by 10 to the minus 19. What that simply means is that the charge of an electron is a value that you don't really have to learn, right? Because it's given to you in the front of your past period. But for now, you'll need it, right? That's the value there. That's the charge of one electron, 1.6 by 10 to the minus 19. And you will recognize that thing there. What is called that thing? Celsius. Very good. A charge in Celsius. Really nice class. Really nice. C is what? Celsius. C is Celsius. And you're sticking with that. Celsius. So charges in Celsius. Anybody else? You would have learned this in coulombs, yeah? You would have learned this in
degrees sign.
exactly. And it's not temperature. So charges in coulombs, right? Yeah. Well, I want you to recognize for yourself that is not degrees Celsius. Right? So charge is measured in coulombs. Right? You would have learned this in the beginning of Form 4. Right? So charge is measured in coulomb, capital C. Let's make a note of that, please. COULOMBS. Huh? Yeah, just young man behind it. He didn't recognize those words out there. Okay. All right.
No offense, it's a bit handwriting terrible.
It's terrible.
But no offense, with respect now.
All right. Are you on me now? I take my thing, you know. I take my thing. My handwriting bad. All right, all right. I take my thing. I take it my thing. Go ahead, Hugh, sing our next song. Right, next thing. Like charges repel, unlike charges attract. Okay, right? While we're here, before we move on, as I told you all before, charge is measured in coulombs, capital C. You all can see that? Write this down. The SI unit for charge, the symbol for charge is capital Q, right? And Q is equal to I by T. So Q is what you call charge, measured in coulombs. You're writing a piano. I is current, measured in amperes, and T is time, measured in seconds. All right, Sean, so put up a passive of now. Put up 2004. You done? All right, I'll check it this one. Put up 2004 from a paper 2. Yeah. Keep pass paper 2. Yeah. All right, pull up 7. Okay, so this is our first relationship that we'll learn about charge. Charge is equal to current by time. Okay. How many types of charge we have again? Keelan? How many types of charge? Positive and negative. Nice. Excuse Malachi, right, isn't it? Just making sure. right? Let's just do one example on this now. Easy example, real easy, right? If charge, sorry, find the charge, on a particle if a current of 4 amperes is flowing for 2 minutes.
Current of 4 amperes.
Current of 4 amperes is flowing for 2 minutes. So I want you to find Q. Take your time, look at the formula. What's the first thing that we do after we get the formula?
Okay.
Right, and what you very good.
Underline what the-
And then what else?
Right on the phone.
Write the formula and then make sure everything is in correct
Units.
SI unit.
SI unit. So we
S-
transform the minute into second.
Very good. What's that? Come on, take the rule in here. They have too many people, right? Q is equal to IT, right? Q is equal to IT. Yeah, message answers. I is 4 amperes and time is 2 minutes. Can we work in minutes? No, we had to work in seconds. So that'll be 2 by 60, which is 120. Okay, nice. So we'll get current, which is 4 by 120, which is 408 coulombs. Right? Okay, boy, and a rule to do, right? Right, nice Ishana, nice Katrina. Sahara, nice. Don't forget the SI unit, right? Viraj, you got that? Christian, you all got that? Well, okay with that, just a quick little intro to that, right? Everybody okay with that, right? One last one. One last one, right? How much current? Yeah, you can message this one, Malini. How much current? That's the I value, right? How much current can one electron? How much current can one electron produce? How much current can one electron produce if it is moving? If it is moving in a circuit for 2 hours. Kind of hard, be careful. How much current can one electron produce if it is moving in a circuit for how much hours I said? 4 hours. Yeah, one electron, right? I said 2 hours the first time, right? I said 4, okay. Anyway, leave it as 4. Leave it as 4. Leave it as 4. I just pass. I'm going to see the answer. Online message answers. Christian. Message answers. Viraj, are you there? Viraj, again, my mother.
The answer is 480 coulombs.
Viraj. Yeah, the last one was 40 coulombs, yeah. Come, Mr. Viraj, some other answer now. One charge of electron flowing for 4 hours. How much current is that? Yeah. Yeah, it's done good watch. But video, let's just back up, don't forget. What the charge of one electron? 1.6. Right? Then final time. So you got something there. That's how we did it up, right? Right, let's check it out. Yeah, I don't know. Oh, it's time. Your time is up. Right, so Q is equal to IT. I asked for current, so current is equal to charge over time. We know that charge is equal to 1.6 by 10 to the minus 19. Really and truly it should be negative, but it wouldn't really affect charge too much, right? Time is 4 hours. So it's 4 hours by 60 minutes by 60 seconds. How much is that? Sorry? 14,400. So now we're going to take 1.6 by 10 to the minus 19 and divide it by 14,400. And that will give us the value in amperes. Let me see if Viraj sent me anything. Nope, he just sent me I am here. Thanks, Viraj. How much you got? Katrina got that. How much you all got? 1.11 by 10 to the minus 23. Nice. So a real small current. One electron only doing that amount of electricity. So if your current here is how much? What's the electricity flowing in some of these here? Like 20 amps and 40 amps something. Imagine how much electrons you will need. Okay. All right, nice. That's to give you a little idea about those things, right? Christian, follow what we did? Christian, Jaden, you'll follow what went on there? Right, I'll start this turn on video thing now. It will take it long. All right. Last thing before we wrap up. Last day this one of the simulations I showed you all had charging by friction, right? So I just want to explain charging by friction, and that's it, right? So when a polythene rod is rubbed with a piece of polishing cloth, the electrons, and again, I want to point out that only the electrons move. So when you have a piece of cloth and you're rubbing against a rod, the electrons move from the cloth to the rod, giving the rod a negative charge. So wherever the electrons go will become negative. Everybody okay with that? And wherever the electrons left from becomes what, Kilon? Positive. Nice. So the cloth loses positive. The cloth loses electrons and therefore becomes positively charged. That's okay? Yeah, no? Easy, right? If a perspex rod is rubbed on a piece of polishing cloth, electrons move from the rod to the cloth. What does that mean? It means that different materials, right? Some materials will accept electrons, some will remove electrons, right? So in the first case, polythene, right? The polythene accepted electrons. Okay, it took the electrons from the cloth, and the other way around with the perspex. Okay. All right. Charging is due to the movement of electrons only, which are relatively small and relatively loosely attached to the outermost parts of the electron. Right. So all the saying there is that the electrons moving. Right. The outermost electrons are not really attracted too much to the nucleus. Those electrons are the ones that moving around. That's okay. All right. And last thing. Something called charging by induction. So watch this here. Initially, those metals fails. Are they charged? Look at the metals fails. Are they charged? Nope. It says uncharged here, molecule. Right? So they are not charged. But look at this here. If I were to bring a positively charged rod, right? What happens to this sphere? They get charged. So all of the electrons move to the left. So this side of the sphere becomes negative. This side here becomes what? Positive. That will now induce a negative here. And as a result, a positive there. You'll see that? So the electrons kind of move to one side. That is called charging by induction. The first one was rubbing by friction. The second one is charging by induction. Okay? Last thing, when the spheres are separated, the charges are equally distributed. Okay? So you have negative on one side, equally positive on the next side. Everybody okay with that? That's called charging by induction. Your homework for me is to read up on the applications, both good and bad, of the electrostatic phenomena. So please read up on insulators, read up on the electrostatic precipitator, car painting, electrostatic copiers, and the lighting conductor. What I will do when they come next day, you'll come from the class and I'll explain it and I'll record you. And I'll post you up. One time. Second and to the page on the handout.